So one of the first slides I will show really talks about, it's sort of personal, it talks about my own personal journey in this subject called blood compatibility. And if you look into the literature, the first thinkings of blood compatibility were published about 1940 or so. The first few papers came out on this subject. I started myself on this area in 1972 with working on the artificial heart. By the 1980s, the medical device industry had sort of coalesced into let's call it a cohesive industry, and the medical device industry began really thinking much more formally about thrombosis, clotting, and here we are in, so that was the 1980s, where there's tremendous development in many commercialized cardiovascular devices. Here we are in 2022, and the big question I'm going to ask is, really, what progress have we made? One of the missions, maybe a vision, maybe an aspiration of our Center for Dialysis Innovation is eventually to get to a wearable, truly wearable artificial kidney. And as you could imagine, a patient with a wearable artificial kidney might dialyze 12 hours a day. It's not unreasonable to think about. Okay, great. Okay, and I think I can advance them myself. So I also have quite a few co-authors, and I just can't introduce all my co-authors, but this is a wonderful team effort here. So again, I talk about this long journey from the 1940s to my start in 72, 1980s, the really development of the cardiovascular device industry, and now asking this question. And in our Center for Dialysis Innovation, we have this aspiration, this vision of a wearable artificial kidney, and simply with a patient doing very long-term, much longer dialysis than we would do today, which there are many, much literature demonstrating that a longer, slower dialysis probably has excellent outcomes for the patient, or better outcomes. So that part is good, but we just can't keep a patient out in the world with a device anticoagulated with the heparin that we use today. There are a number of different risks and expenses that are associated with that. So we simply need better blood-compatible surfaces. And this slide, again, I could spend quite a bit of time on it, but I'm asking, is blood compatibility solved? I talked about the long history of people working on this, and yet you look at so many of our devices today, and they all require anticoagulation or have thrombotic complications. So the answer is no. In spite of all these years, we have not solved the problem. I went into Google Scholar just the other day, and I entered since 2021 with blood compatibility in quotation marks, which means it'll look for won't look for blood and compatibility, it'll look for only blood compatibility. I got 4,880 hits on the subject of blood compatibility just since 2021. And looking at the different types of polymers or materials that this is just a very partial list. So many different materials are described as, papers are titled blood compatible material. So if we look at this, some are hydrophilic, some are hydrophobic, some have both types of qualities, and so many different classes of materials there are listed. Read the titles of the paper, blood compatible. So we could ask a question, is everything blood compatible? You'd almost get that if you really did an analysis of the literature. And if everything is blood compatible, why do we not have good clinical solutions yet after 80 years? That's where we're going. So I have been thinking a long time toward a consistent, cohesive theory of blood compatibility. Now, just in sort of a tutorial sense, you go to the left side of this slide, and we have blood contacting a medical device there. Within 1 second is an adsorb protein layer on the medical device. And so, in essence, the blood never sees our medical device. It sees a adsorbed, a sticky protein layer on the surface. But once there in the blood, there's really 3 mechanisms that the blood clots by. On the very bottom, in arterial, fast blood flow, blood platelets are important. In the middle, in venous or slower blood flow, what we call the intrinsic system, the system that takes a protein, fibrinogen, and makes fibrin clot, is important. And also the complement system of white cells intersect in very complicated ways with this whole system. So I'm going to throw up 6 points that are very important to me, and then I'm going to throw on a 7th point. For one thing, there's no one blood compatibility. The body has multiple mechanisms to induce clotting, and we have to think about materials that address these multiple mechanisms. Interfacial proteins are the key. The blood never sees our materials, it sees proteins. One of these proteins, albumin, particularly in what we call an unoxidized form, is totally inert. I call it blood compatible, but it's really quite inert to blood, and that's the major protein in our body. Another protein, fibrinogen, has a bad reputation, and yet there are so many incidences where fibrinogen can be relatively inert or almost good rather than bad, and that's a pretty complicated literature in itself. The best blood compatible surface, a healthy living endothelium, the healthy lining of your blood vessels. And I'm going to skip the non-adhesive encounters thing, but number 7 is if the complement system or the inflammatory system are triggered, well, all bets are off. Those enter into very complicated ways to potentially induce thrombosis. Go back to 1972, and this paper came from one of my sort of mentors and colleagues, Lawrence Harker, a hematologist here at the University of Washington, and talked about platelet and fibrinogen consumption in man, demonstrating that in the venous system, fibrinogen is important. In the arterial system, platelets are important. So many coagulation mechanisms. Why should we think one is important? I talked about proteins. There are a lot of proteins in the blood. Here's a few of them. Albumin in particular is a bland protein, and fibrinogen is often associated with coagulation. And so those two I'm going to really address. Another pioneer in the field, Don Lyman, who passed away relatively recently, actually retired to Olympia, Washington, here in his retirement years, and I've known him since the 1970s, knew him, pointed out in 1974 in a paper that high albumin on the surface would be the area of non-thrombogenicity. Seems good. So albumin is an inert protein. Higher albumin to fibrinogen ratios are desirable. One protein, bigger proteins can push smaller proteins off the surface. So the ability of albumin not to be displaced is desirable. Damaged albumin must be replaced. And fibrinogen epitopes are responsible for strong interactions with platelets. If these epitopes on the fibrinogen molecule were not expressed, that would be good. So we do an experiment here called a protein elution experiment. And basically, if that blue rectangle is a surface of a biomaterial and proteins absorb, we can also absorb iodine 125 label, radio labeled proteins. And we can, for example, elute them with a soap, sodium diacetyl sulfate, and see what's left. So we're asking this experiment that I'm going to show you how tightly is the protein stuck to the surface. Well, we have some fluoropolymer surfaces. This was some work published by some of my colleagues a few years ago. This looks at albumin retention on a surface and shows that some of these new fluoropolymer surfaces that we invented here have very high retention of this albumin protein. Remember, albumin's good. Other surfaces, even Teflon, has 27% albumin retention, where this fluoropolymer that we developed from a plasma deposition has 95% retention. So what I'm going to talk about is basically results that have happened from our blood compatibility team over 5 years in CDI. That's led to 2 polymers that have shown exceptional blood compatibility in numerous assays. One is called carboxybetane, sometimes abbreviated CB, and another is a plasma-deposited fluoropolymer that I mentioned. So this work is some work from Sherry Liu. Sherry is here helping us actually get organized in this event. And Sherry has shown that the fluoropolymers bring down more albumin and furthermore bring down less fibrinogen, and this is very desirable. A lot of complicated things in this slide I don't have time to go through at the moment. The other polymer is this carboxybetane, CB polymer. It's called sphincteroionin. It has equal numbers of plus and minus charges on it. And it also has a photoreactive group that allows us to treat surfaces with this. And there's a little diagram down on the right that shows how much protein absorbs to this polymer. Uncoated has the big orange bar, lots of protein. And we coat it with this material, and the proteins drops to very, very low numbers. This is some work from another of our PhD students, Kyung-Hoon Kim, and he's done a number of different assays looking at the intrinsic clotting system, the protein clotting system. And in every case, the fluoropolymer, that's the circled purple boxes there, in every case, the fluoropolymer and the carboxybetane show the best performance in low generation of this thrombotic protein thrombin, in increasing clotting time. We wanted the blood to clot slowly as possible, and activation of this particular protein factor. Here is some measurements actually coordinated by Dr. Anna Galperin, who is in the room here, looking at the CB polymers and looking at platelet activation. And again, in every case we've measured, the CB polymer comes out better than the control materials. The control here, this was a mock dialysis loop. So we're looking at polysulfone hollow fibers, we're looking at PVC tubing. And when we coated this all with CB polymers, we got a much lower platelet activation. And also much lower activation of this blood system, the complement system that ties into the immune system with the CB-coated material. So the conclusion, multiple assays are needed to establish blood compatibility. 2 polymers, the CB and this plasma polymerized fluoropolymer, consistently perform better than control materials. And there would be applications for either or both these materials in dialyzers, in tubing sets, in sensors, in central venous catheters, and we are working to see these coatings will go on into, I think, future dialysis devices. Just to finish up, in 1858, Rudolf Virchow, who's sometimes called the father of pathology, published his famous first pathology textbook. And Virchow said the important things in worrying about thrombosis are the nature of the blood, the nature of the flow, and the nature of the surface. That was in 1858, and Rudolf Virchow was right on. And let me just thank part of our team. I might have even left off some people, but that's a pretty recent picture by the cherry blossoms that bloom here on our campus. Thank you very much.